Okay, this is our last major section of limits. So we are going to review determining vertical asymptotes, review horizontal asymptotes, and really the heart of this lesson is to determine properties of infinite limits. But I feel like you need a review of those to kind of help all of this make sense. So a limit in which our function increases or decreasing without bound as x approaches c is called an infinite limit. So, infinite limits, or when they equal infinity as we approach some c values, they technically do not exist. Remember, we've talked about that. We use infinity so we can be more accurate in describing how the limit doesn't exist, but we can get a picture of what the graph looks like. So, that is because the limit must equal a constant number. So, I keep talking about this, and I know you don't really understand why, but we want to use infinity to describe it, even though it really does not exist. All right, so vertical asymptotes. Remember, those are imaginary boundary lines, and graphs usually like approach infinity around them, and that's when we had rational functions where our denominator equals 0 because it's an undefined value and mathematically that's how they occur. So I've got three different functions and we want to find out where those values are. So we set our denominator equal to 0. We can divide both sides by 2, add 1, and so we would have a vertical asymptote at x equals 1. Here, sign is a little differently. Remember, sign, as a review, keeps going. That's why I'm going to draw these little arrows. But this is 0, pi over 2, pi, 3 pi over 2, 2 pi. And so what's happened is it's going to be every pi, positive or negative. And so if you remember how to write this, it's a little tricky, but x equals pi plus x times n, where n is a number, 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is all real numbers. Okay. And our last example, remember, if we can factor and reduce, we get a whole. So I do want to factor the top. So we don't want to just set the denominator equal to 0. So the bottom is perfect squares. It's a lot quicker to factor. The numerator, the factors of 8, that will give me a positive 2. I've got 4 times 2 is 8. And if I want positive 2 times negative 2, I would get negative 8 to multiply and positive 2 to add. So the terms that reduce produce a whole. The denominator that's left produces the vertical asymptote. Okay, see the difference? That's why I mentioned this. So x equals negative 2 is our vertical asymptote. Oops, I didn't write it over here. All right. Properties of infinite limits are the same as our regular limits. So adding, subtracting, constants, they all work. So we said f of x equals infinity. So I'd have infinity plus or minus L. Infinity, if it's positive, it'll be positive infinity. If our limit is negative, then we're going to end up with negative infinity. Our quotient, I'd have infinity over our limit, which infinity over any number is going to be infinity, like infinity over 5. This is so large that it's going to equal the bottom. And same idea here. I've got L over infinity. Now, we have a really small number over something really large. I think of like 5 over 1 million. Well, that's really, really small. Okay? So for my quotient, I kind of do these differently. So I say we want to look at the highest power. I'm going to come up with 3 of my own rules. They're not really my own. I learned this when I took calculus, but if the numerator powers is the same as the denominator, then you're going to use the coefficients. That's your limit because it's the ratio of those, okay? If our numerator is smaller, that's like this, we get 0. And if our numerator is larger, we get either positive or, I like to write it or, a negative infinity. And you want to check the powers. This will make more sense, okay, on the problems. So this looks really, really complicated. I promise it's not. So they're going to give us a graph of this function because, well, 3x over x squared plus 1 is kind of tricky. So let's say they also gave us this table of values. Notice we don't have any undefined values here because our denominator will never equal 1. We don't do imaginary numbers in calculus, okay? Not in Calc 1 or 2, and I totally forgot what I learned in Calc 3. So the limit as x approaches negative infinity, so remember these are our x values, we want to be looking over here because this is where negative infinity for x is. And we say, oh, well, it looks like they're leveling out, and we can use our table to verify, yep, leveling out at 3. That's not 30, that's a 3, sorry. Let's make that, okay. And then our limit as x goes to positive infinity, well, we want to be looking right here. Ooh, those are leveling out, and we look over here and we say, yeah, they pretty much are, okay? So that's what I mean by limits of infinity. It doesn't mean our answers are infinity, it means that's where we're looking on the left and the right. And that's called end behavior, which end behavior actually refers to our horizontal asymptotes way back in Sec 3. Okay? So, theorem limits. This is kind of what I did. Up here. I kind of just skated to it. Right there. All right. So let's look at our powers. And I'll write them here. So if they're equal, you're going to use coefficients. If our numerator is bigger, it's plus or minus infinity. If our numerator is smaller, I know I'm not doing it in the same order. Okay. All right. So let's look at our powers. So our powers here are the same. So it's really going to be, after we get really, really large numbers that we're plugging in, these become insignificant. They really go to nothing. So I use my coefficients, and I've got 2 over 1, which is 2. It's really just the ratio, like 2 million over 1 million, 2 billion over 1 billion. That's what you have to think of. We're plugging in large numbers, okay? So it's the same thing here. We're plugging in 10, then 100, then 1 million, then 3 million. So these become nothing. My numerator power is smaller than my denominator. So it's always going to be smaller on top. That's how I remember, oh yeah, smaller on top means it goes to 0. And my last problem, we can ignore all those. My numerator power is higher. So my choices are plus or minus infinity. So this is what I mean. If we're going to negative infinity, then I want to use x equals -1 because I just need to determine the signs. So I've got 5, and you want to use the coefficients too. A negative number and the 4, because those coefficients do impact this term. So 5 times that would be a positive. And notice I don't care what the value is. It's always going to be a lot larger on top. That'll be a positive times a positive. And so that's how I know this one goes to positive infinity. All right, so see, I don't even waste time with the real calculations. We're just trying to figure out the signs. Okay, so now we have some different strategies. So with trig functions, it really depends on what trig function they give me my strategy. So on part A, since this is just sine, I know I'm going to keep going for on and on and on forever. And so it's saying like, hey, when you get to infinity, can you predict what the 1y value is going to be? And we say, well, I know it's between 1 and -1, but it's just going to keep going back and forth and back and forth and back and forth. So remember, that was called oscillating. So since this function oscillates and it doesn't converge to one y value, our limit does not exist. Does that make sense? Okay. Now, the second function is completely different. So on this one, I've got the sine of x over x. So this is where that squeeze theorem is going to come into play. And I know we didn't really talk about that, but this is where that idea, we'll see how it's used. So I want to break this up into two functions. So I can think of this as the sine of x, and then there's like a 1 here, so I'm going to break that up because we're multiplying it. So I want to break that up into 1 over x, and then I want to do the opposite, negative 1 over x. And I know this doesn't make any sense to you right now. So what we want to do is we've got these ideas. So really roughly, we've got 1 over x, so, and I'm blowing this up. I mean, this is really tight, but our goal is infinity. Okay, and then we can use negative 1 over x, which is the reverse. And so what that does is if I take sine, the idea is that that sine wave, and I know I'm not drawing this very accurately. Oops, it's because I would have went up there. There we go, I should have started in the middle. Is going to be in between those two functions. And so what happens is when I look at those two functions as we go to infinity, they're really, really close to the axis. So as my boundary, the squeeze theorem says sine is in the middle of there, and so it's got to be in between those two functions, which is really, really small. So we get 0. Okay? That one is tricky. I totally get it. We're going to use a graph for e to the x. So e to the x is exponential growth. Remember, e is about 2.71828. So if I plug in 0, anything to the 0 power is 1. And if I plug in 1, I would get 2.71828. And then it grows. It does have an asymptote, horizontal asymptote at y equals 0. So from the graph, and this is one that you should have an idea of what that graph does look like. So as x approaches infinity, what are my y values going to? Well, they're getting really big really fast. And then as x approaches negative infinity, well, they're getting really small, but not much smaller. They're never going to be less than 0. The natural log is a little harder to remember. You have a restricted domain because we can't take the natural log of a negative number, so no negative numbers. We actually can't, it's like e to what power gives you 0. We can't have 0. So it always has to be positive. So x has to be greater than 0. And so what we remember is that there is an asymptote here. If I plug in 0, remember, natural log is log base e, so it's saying e to what power gives you 0. Well, oh, I don't want 0. Never. So d and e. Undefined, whatever. 1, natural log of 1, is log base e of 1, which is saying e to what power gives me 1. Well, remember, any e to, or anything to the 0 power. So 0. So we get 1, 0. And it's gonna keep rising, but it doesn't rise very fast. This one's not used as much. I don't know if I memorize it, but I do know these connections in order to get it in the future. So as x goes to infinity, we are going to keep growing even though it's not growing very fast. And 0 from above, notice. So we want to look at 0, but from the right, and it's going down. So that's negative infinity. Okay? If they give you just a function, it'll be a simple function. Like they don't usually have numbers here, but you should be able to generate that without a graphing calculator, just so you know. Okay, so give your limits of infinity a try. It should be quick, so let me know if you have any questions.